We get going right now. Question 3. A team triathlon is a race involving swimming, cycling and running for teams of 3 people. The first person swims, the second cycles, the third person runs. The winning team is the team that completes all 3 stages of the triathlon in the shortest time. Wow. 4 friends are training to enter as a team for the triathlon. They need to choose who to enter for each stage of the triathlon and who to leave out. Oh. The table shows the times for each of them to complete each stage in training. Complete a dummy column in your table. Apply the Hungarian algorithm, reducing columns first. Make sure that the values in your table can all be seen. Write a list showing who should be chosen for each stage of the triathlon. What's the minimum total time in which the team can expect to complete the 3 stages? Just another thing, I want to really kind of stress that don't just get drawn into looking at a question, starting to read the question, think, oh yeah, I know what I'm doing, and dive into it, without reading that actually they want you to write a list showing who should be chosen for each stage, and they want you to give the minimum time. Okay, so it's not just dive in and finish the algorithm, it's finish the algorithm and complete it by doing the last little bit of tying up the loose ends. Now we need a dummy column in here because one of the people isn't going to be chosen, so we need the kind of the reserve, the not doing something column. You can put pretty much whatever number you want in here as long as it's bigger than 0. What you don't want to have is the chance of somebody being chosen to be the reserve when actually they would have been better chosen for something else. So we should have this as a big value, either the biggest value in the table, which would be 82, or a value that's bigger than that just ensures that nobody gets picked. So 82 or 100 or whatever value that you like. I think I put 82 on mine. I did when I did it. And then the question said, start by reducing columns. So I'm going to reduce the columns. I'm going to label what I'm doing. I'm going to this network first. Reducing the columns means subtracting the smallest value from each column. So we've got 25 away from this one. We've got 70 away from this one. And we're going to take 45 away from that one. And of course we're going to subtract 100 from that column. So we've reduced the columns. Now we see the reason why they told us to reduce the columns first. Because at this point now, everybody should have the same table, and there's no point in reducing rows because there's a 0 in every row. So we can't reduce the rows, that won't make any difference to it. That is our reduced matrix. At which point we do our thing with our ruler where we try to see what's the minimum number of lines we could cover it with. Well, obviously we can knock out all of those zeros with 1 line. It then makes sense to knock out 2 zeros with that line and 2 zeros with that line. So that's the table that we're left with. You look for the smallest uncovered element in that table, which is 3 there. So the value we are augmenting by, E, equals 3. I'm moving to this table down here now. And augmenting means we subtract that from every uncovered element. Any element that's covered once, we leave as it is. Any element that's covered twice, we add the augmenting value to that. So that would be the first 2 rows. And we've then got 17, 3, 5, and there's another 0, and then we'd have 15, 0, 0, 3. So there is our new table. What are we going to do with this? Can we, how many lines would it take? Try it with your ruler first. Well, just actually a quick glance shows us that we're not going to do this with any less than 4, are we? Because as soon as we as soon as we look at this, we can see we've got, is that a faint line? No, it's quite a thick line. We'll use that one again. We can see that we've got 0 there, the only 0 in that column, only 1 0 in that column, only 1 0 in that row, and then that leaves us with that 0 there. So actually we're going to be able to do this, aren't we? We have to use 4 lines to do this. You can't do it any fewer than 4 lines, which I'm not going to. It gives us the chance to take that 0 must be used, that 0 must be used, that one's the only one in that row, and that leaves us with that 0 up there, and we appear to have a solution, which we need to finish off by writing the bits of words that we needed. So we have, I haven't copied this bit, but it was on the bottom of your page. You had swim is Gary, cycle is Isabel, and that's quite good, isn't it? Because Isabel on a bike, yeah, you use it to warn pedestrians. Isabel on a bike. It was a joke. And Fred is running, and we're going to go back and look at our original network and see what numbers these related to. So that one was a 25. Cycling, Isabel was a 70, and Fred running was a 48, and so that gives us a total of 143 minutes from the original thing. Brilliant, eh? Nice and easy. Right, so then the question said, what did it say? The day before the triathlon, the friend who had been chosen to swim is injured. Oh no, and can't compete. Poor Gary. If the reserve takes over the swim, how much longer can the team expect the triathlon to take? Notice it's how much longer, not how long can it be. How long will it be? I'm not saying that very well. The question didn't say what's the new time. It said how much longer. So, the reserve was Helen, and Helen was 15 minutes longer. Was she? Which one was it? Oh, it was Gary. It was 20 minutes longer than Gary. So Helen will take 20 minutes longer. That's what they wanted, the answer. Then we get the new bits. It now says, remove the row corresponding to the injured swimmer to form a 3x3 table. Apply the Hungarian algorithm to find who should be chosen for each stage to complete the triathlon in the minimum expected time. State this minimum expected time. So you had a new table that had labelled those three. Obviously it hadn't labelled what these were, but this is now Fred, Helen and Isabel, and if we draw a new table, these are the new values. So it was 1 mark, I think, just for creating your new table. So now we're going to see if we can reduce that. I reduced the columns first, because we'd reduced columns first in the previous one. So for completeness, I thought I'd do the same thing. So if I reduced the columns, I got 0, 15, 10, 5, 6, 0, and what's that give us? 3, 8, 0. At which point we notice that actually we've got 2 in that line. We can reduce this further if we reduce rows, or we can dive straight into the Hungarian algorithm. I'm going to reduce the rows and see what happens with that. If we reduce the rows, that one can't be reduced. That one will go to 902. That's 1000. At which point, hopefully, we notice that we'd need to use 3 lines to cover everything there. It's a 3 by 3 table, so we've got 0 there, the only one in that row, 0 is the only one in that row, that 0 is the only one in that column. So we're left with the solution straight away as being Fred is going to swim, Helen is going to cycle, and Isabel is now going to run. And that was 30, 76 and 45, which gave us a total of 151 minutes. And we got a few little checks that our answer makes sense. That should be worse than our original time, which was 143, but it should be better than 20 minutes longer than our original time, which would have been 163. It is better than that, so we're happy that we've used the algorithm correctly to do that. There we go, and that's some marks for some maths.